So welcome to the IBM booth here at GITEX Europe. What we have here is a model of a quantum computer. And quantum computing is a very modern, very new, very different approach to computing. With a quantum computer, it will be possible to solve problems much faster, maybe more accurate or more cost efficient than with traditional computers. To be honest and to be clear, as of today, there is no what we call quantum advantage. So as of today, quantum computers are not yet better than classical computers, but we expect that to happen by end of next year. Yeah, so by end of 2026, we expect to have the first practical use cases where quantum computers are better and provide advantage versus classical computers.
Could I ask what kind of advantages they bring in, or what would be the use cases in the future that will replace this?
Yeah. So we are thinking about three different areas of use cases. The first area is, we call it simulating nature. So that's about chemistry, quantum chemistry, material research, creating better, lighter, stronger materials. For example, for batteries, that also work at lower temperatures. So that is one area. Next area is optimization. Yeah, so mathematical optimization, like routing optimization, optimization of supply chain and such things. So we have one partner that we are working with. They are looking at optimization problems related to a transformation of the energy network. Yeah. And the third area is around machine learning and AI. So we expect that also there will be advantages with quantum computing. And in that area, we expect that to be able to train better machine learning models, so more accurate models with less training data than in the classical world.
As I'm not really an expert here, so I would like to know what the quantum computing brings that makes these differences. What features it has that makes these differences?
So quantum computers are very different from traditional computers. It's not just that they look different, as we can see here, but also the algorithms and the whole logic is completely different than for traditional computers. And in some sense, they are based on the principles of quantum mechanics. So that is a superposition and entanglement. And it is not obvious, but that can be used also to write algorithms for other areas than just simulating quantum mechanics. And so entanglement, superposition, also inference, these are the fundamental principles or capabilities that can be used for specific areas.
Somebody wants to come to this field, is it like they need to study physics, or which background is needed?
Yes, so that very much depends on what area of quantum computing you want to look at. Of course, we need physicists to build quantum computers. Yeah. On the other hand, a big area, the big demand for experts is in using quantum computers, so applying that to industry-specific use cases. And for that, you do not need to understand the details, how a quantum computer is built. We also want to provide APIs for these areas that I mentioned, so that people also do not necessarily need to understand how these quantum algorithms work. Yeah? And so in the future, it will be possible to use quantum computers just by calling an API. Yeah. But still, people need to understand the capabilities and what problems it is well suited for, and to leverage the power of quantum computers.
That sounds really interesting. Thank you so much.
Yeah, thanks a lot.